So, eigenvalues and eigenvectors. Now, many of you are in linear algebra right now, and you haven't gotten this far. No. However, I brought tea. So we're going to get through it together. And it's actually, this is probably the most advanced linear algebra technique that you need for this part of the class. Until you've learned the stuff in linear algebra, this is the furthest ahead you have to be. However, it's not that bad. It's really not that bad. So I'll teach it to you, and you'll learn it again, and you'll learn it better when you are in linear algebra. So we'll just go from there. These two things, finding eigenvalues and eigenvectors, so useful. It's a great tool. So it doesn't just come up here in this class. It'll comes up in vibrations and dynamics a lot. So we will now recall the eigenvalue or eigenvector problem. Okay, so maybe some of us can recall it. Others of us are learning it for the first time. For an n by n matrix A, okay, so you have a matrix A and a vector m and a scalar lambda, this is the eigenvalue eigenvector problem. Okay, it just states that one side of the equation has the vector m, the other side of the equation has the same vector m, and on the left-hand side, we scale it by some real number. So this lambda could be like 5 or something. And when we scale a vector, what are we doing? We're just stretching it, right? So we're either stretching m or we're shrinking m down, but it's in the same direction. On the other side, we're multiplying m by a matrix, A. And that, we're saying, can be equal. They can be equal for certain conditions. And those conditions will define what the eigenvalue and the eigenvectors are. Eigenvalues and eigenvectors are. So, those values of lambda and corresponding values of the vectors m that satisfy this equation are called eigenvalues and eigenvectors. So all lambdas and vectors m that satisfy this are the eigenvalues and eigenvectors of the A matrix. The A matrix, we're using A here. This could be of any matrix, but we care about it in our context because for the A matrix of our ABCD state space model. Okay, so that's what we're going to be finding the eigenvalues and eigenvectors of. Now, all we have to do is learn how to find them, right? Learn how to find, for a given A matrix, how do we find lambda and m, the various values of lambda and m that satisfy. So, finding the eigenvalues. The method is find the eigenvalues first, then find the eigenvectors. Okay, so first we find the eigenvalues, and we can rearrange the equation. So this was the equation right here. We can subtract am from both sides so that we have lambda I minus a. So I had to multiply lambda by I to show that it can have the same dimensionality as a before I can do the subtraction. So lambda I minus a times m is equal to the 0 vector. Okay, so we need to find the lambdas and the m's that make this true. So for a non-trivial solution, this implies that the determinant of lambda I minus a equals 0. Okay, which is great because the determinant, as you guys can remember, we used the determinant last semester. The determinant is pretty easy to compute for most of the matrices we care about. So all we have to do is lambda I minus a, take the determinant. Actually, you guys might recognize this determinant of lambda I minus a equals 0. Does that look like something we've done? In differential equations, we did that. And if, I mean, so for matrices, you may have done it in differential equations, but I also in mechatronics, we did this, but it wasn't lambda we used, it was S. We did determinant of SI minus A equals 0. What did we call that?
Operator something?
S was, yeah, it was an operator. It was an operator form. So what did we call the equation that we got? It's a really important equation for solving differential equations. Characteristic equation, yes. Excellent. It's a characteristic equation. And that is what we're finding here, okay? It turns out, giving away the punchline here, the eigenvalues of the A matrix are the same as the roots of the characteristic equation. Huh?
They have to be because you set it equal to 0.
Yeah, exactly. So they're equivalent, and so this is one of a few equivalencies. So we're going to be finding determinant of lambda I minus A equals 0 a lot. That just comes up a lot in a bunch of different areas, and so this is one of them. So this is the characteristic equation for the A matrix. If we expand the determinant, we get an nth order polynomial in lambda. Always happens, okay? You always get an nth order polynomial in lambda, and set that equal to 0. So we're finding the roots of a quadratic equation, or not a quadratic, a polynomial equation, right? If it's second order, it's quadratic. Ideally, second order, that would be great. Which can be solved for n roots, okay? We're only going to consider the case in this class of n distinct roots. So we're not going to do any repeated roots. All of what we learn can be slightly altered to deal with the case of repeated roots. But in this class, if we're going to be finding eigenvalues and eigenvectors, we're not going to be considering repeated roots. It's just a little bit more complex, but I think if you guys get this, you could always extend your knowledge to those cases. And the book, I think, does not consider it either, but if you ever find yourself in that situation, there are plenty of sources for finding how to do this. So. Great. So finding eigenvectors. So we got the eigenvalues. It was easy. All we needed to do is find the characteristic equation and solve for lambda. Now, finding the eigenvectors is the part that a lot of people struggle with this part. And I don't think that confusion is necessary. It's just the problem is there are an infinite number of solutions, and that trips people up a lot. That's the part that screws people up, is that there are an infinite number of solutions, and so they have a hard time recognizing any particular one of them. So let's explore that a little bit. It's really not it's not that bad, and if you follow this sort of method, you do a few problems, I think that it becomes pretty clear how to find them. So has anybody ever had Tulsi tea before? Do you guys know that herb, Tulsi? So I have this tea. There's a tea store in downtown Olympia that has this Tulsi ginger lemon tea. Oh, it's just amazing. It tastes like earth. It's great. It's great. Yeah. I like that. It's like, you know how beets taste like dirt?
I love beets. But
yeah, but they're great, right? Yeah.
I would say they're smooth.
Snow washes before you
Light on the palate.
Yeah. It's almost like they've spent their whole lives in the dirt,
It's like they're
and they've just brought it in. Okay.
Well, in that sense, onions and potatoes should taste like dirt.
Yeah, they just don't, though.
And carrots.
Yeah. Potatoes I can see a little bit, but beets definitely, for sure. Beets are amazing. What?
Eigenvectors. Beets are only eigenvectors.
Tulsi ginger lemon tea, though, telling you. You need to get that. All right. So finding eigenvectors. All right. So, oops. There we go. Each eigenvalue has its corresponding eigenvector. We find the eigenvector mi, so it's going to have several eigenvectors in the general case, for an eigenvalue lambda I by substituting lambda I into star and solving for m. So star was this this equation up here, solving for m. But of course, star is equivalent to star prime, which is another form that we might want to use as well. So either one is equivalent. So what we're going to do is we're just going to learn this by example. Okay? So we're going to do example. Oh no, I didn't hide this. You guys can see all of this, can't you?
Yep. Well, it's not printed. I don't
Well, I
think.
mean.
It's not printed?
The whole time, but
No.
it's printed too.
What's going on here? Time out. My apologies for the delivery on this. Yeah, but the problem is then it's going to overwrite, so I have to quickly do this. So I got to delete some things. No, I'm giving it all away. Don't.
Close their eyes.
Yeah, close your eyes.
It's the
All right. Whew. Good thing I was so quick that you couldn't see anything, right?
Mm-hmm.
All right. So, let our A matrix be this nice 2 by 2 matrix. So, how many state variables are we going to have? 2. We want to find the eigenvalues and eigenvectors of this A matrix. So, let's think about it for a minute. What do we expect to happen in the 2 by 2 A matrix case? How many eigenvalues, that's the first thing that we should think of. How many eigenvalues do we think are going to come out of this? 2 eigenvalues. And the reason is, so you could think about it in terms of the equation up here that is going to take this determinant and you're going to end up with a lambda squared showing up. That's one way. Another way to think about it is that we had already drawn this equivalency between the characteristic equation and the the characteristic equation of higher order input-output differential equations, where we had a characteristic equation in those, to this characteristic equation here. And if it was a second order system, remember that the characteristic equation came out to be second order. If it was third order, it would be a third order, and you would have that many roots of your characteristic equation. So, same is holding true here. Our characteristic equation has 2 roots, and so we have 2 lambdas. And I said they're all going to be distinct in this class, which is nice. But in general, in your linear algebra class, for instance, you may or may not have them be distinct. And your eigenvectors, each eigenvalue has an eigenvector that it corresponds to. It actually corresponds to any scaling of that eigenvector as well. But we'll get to that. We'll cross that bridge when we get there. I'll talk a little bit more about the scaling. So let's find the eigenvalues. So if we take our equation that we drew up here, determinant of lambda I minus A equals 0, that's our characteristic equation that we're going to use to find the eigenvalues. So let's just use that. So lambda I, the determinant of lambda I minus a. Determinant of lambda I minus a equals 0. So this is, let's rewrite this with the matrices all plugged in. So this is equivalent to the determinant of lambda I is going to be the scalar lambda times the identity matrix, which is 1, 0, 0, 1 in the 2 by 2 case, and it has to match up with this A matrix. That's why we chose 2 by 2. And the A matrix is 2, negative 4, negative 1, negative 1, right? And that has to be equal to 0. Okay, that's good. So the lambda multiplies, so it's a scalar multiplying a matrix, so it multiplies each element of the matrix. So it's lambda times 1, lambda times 0, 0, lambda times 1. So we're going to have the determinant of, I'm going to do the subtraction too in this step because it's a lot of rewriting. So determinant of, so it's going to be lambda minus 2. We're going to do element-wise subtraction here. So lambda minus 2 is the first term. The next term is 0 times lambda, which is still 0, minus negative 4, which is positive 4. Then we have lambda times 0, so 0, minus negative 1, which is positive 1. And our last term is lambda times 1, so lambda minus negative 1, which is plus 1. So lambda plus 1. Okay? Now we have to take the determinant, which I expect you guys to be able to do a 2 by 2 determinant by hand on an exam. I would prefer 3 by 3, but I'll just let you guys stick to 2 by 2 because it can be a little hard on 3 by 3. It's just a lot of writing. So. But 2 by 2 is really easy. You just have to take this term, multiply this term, and then subtract this term multiplied by this term. So it's like this X thing that you draw. In my mind, that's what it is. So we have lambda minus 2 times lambda plus 1 times lambda plus 1. And subtract 4 times 1. So minus 4 times 1. That has to equal 0. And lo and behold, we have our characteristic equation written in a nice polynomial form. Lambda squared minus lambda minus 6 equals 0. And solving that, I would recommend just quadratic formula, but you can factor, you can try to factor and stuff if you want. I don't even think about it. I just go straight to the quadratic formula. So I say lambda equals, so help me out with the quadratic formula. Negative 1, so it's 1. And I like to write the first term by itself. So I divide it by 2a first. So 1/2 plus or minus 1/2 again times the square root of
1 squared, negative 1 squared.
So we have b squared, so negative 1 squared, so 1. Right? And so this is 1/2 plus or minus. This is square root of 25, so that's 5/2, which is equal to 3 and -2. So I'm going to write lambda 1 comma lambda 2 is equal to 3 comma -2. So I have defined lambda 1 to be 3 and lambda 2 to be -2. Okay, that's just sort of a standard notation for writing multiple solutions. Now, we have our eigenvalues. So this is actually one of the things the question asked for. What are the eigenvalues? So we'll mark that as one of our answers. And then we'll take a sip of Tulsi ginger lemon tea.
You should write that in the steps.
You know, I should get sponsored to like push products in my lectures. Oh man, that would be hilarious. Product placement, just like pull up my mug with a brand on it. All 23 views. Okay. Eigenvectors. We need to substitute each lambda into, we're going to use the lambda star form because I think it's a little bit easier when it's in that form. You can do it with lambda, or with the star as well.
What is lambda star?
Sorry, I mean the star equation.
Oh.
Not the star, lambda star. I don't know why I said lambda star. The star prime is the one that we're going to use. Star prime is this one. I like this form better to do this. So essentially it's lambda I minus a times m equals 0. So let's do that for the first lambda. So for lambda 1 equals 3, this is our first eigenvalue. We're going to do this. So I will now plug it into that equation directly. So lambda I minus a. So lambda I is going to just put whatever that lambda is along the diagonal of the identity matrix, right? So we're going to have 3, because that's our lambda. Lambda 1 is 3, 0, 0, 3. So that's just lambda I, right? So lambda 1 I. Minus the A matrix, which is our original A matrix, which was 2, -4, -1, -1. And we multiply this vector m1. So we're going to find an m1 equals what? We don't know yet. So we are going to write it m1 as 2 unknown values of m1. So we're going to call this m11 and m21. Okay? Equals the 0 vector, which in this case is 2 by 1. And we're trying to find what m11 and m21 need to be. Okay? So let's simplify this part, since that seems like the easiest way to start. So I will say this implies that let's build this matrix that comes out. So 3 minus 2 gives us what? 1. And 0 minus -4 gives us 4. Let's do the second row. What's this term going to be? What is 1? And what's this one? 4. That's interesting. So I don't know how many of you have been exposed to the idea of solving algebraic systems, linear algebraic systems of equations using matrices. But if you have been exposed to that, you probably would recognize that this has an infinite number of solutions to it. And let's think about that. And this is always the case with eigenvectors. There's always an infinite number of solutions. But that doesn't mean that you can write down any solution. Okay? They're specific infinite number of them. So what we want to know is, so M1 equals, and we're going to say we call it M11, M21, and we need to populate it. So I'm going to leave a little space here, and I'm going to draw my column. So I need to put two values in. Now, if I was to plug in, let's try to satisfy the first row equation first. So say M11 was, I chose -4. Okay, let's try -4, and then M21 was +1. That would make that row 0, right? Because it would be 1 times -4, should be -4, plus 4 times 1, which is 4. So -4 plus 4 is 0. 0. So that would satisfy. So let's just write that solution in. So we had -4 and 1. That solves it. But let's try, for instance, let's try 4 and -1. Right? Because you could put 4 in here, and it would be 4 times 1 plus 4 times -1, which would be -4. So 4 minus 4 is 0. So that's also 0. And it turns out you can multiply this by any scaling factor and still have a solution. Okay? So what I'm going to do is I'm going to just draw an alpha here and just say alpha is any real number except 0. Well, actually, it does actually include 0, right? It's just a trivial solution. So that is actually true. Okay, so this is an eigenvector. Any multiple of it is an eigenvector as well. So oftentimes people will write this with where they all are divided by a scaling factor that will make the highest one 1, or they'll make it so that the norm of it is 1. Doesn't matter. Doesn't matter at all. You can choose any eigenvector. Still a solution. So I will just go on to say, because I know we're running out of time here. So I'll just say that lambda 2 equals -2, and by the same process, but I will write the first step down. By the same process, we plug in lambda 2 equals -2, then 0, 0, -2, and then we call this M12, M22 equal, sorry, I totally screwed that up. Erase.
I can erase
Oh. 2, -4, -1. I forgot which equation I was writing. And we multiply that by M12, M22 equals 0 and 0. And oh, what the heck. I'll just go ahead and write this. -4, 4, 1, -1 is what we get if we say -2 minus 2 is -4, etc., etc. Multiplies M12, M22 equals 0, 0. Okay, so now we've got to solve for M 2, so I'll get rid of that. So M2 is equal to, M12, M22, and the values are going to be some scaling factor. We know it's always going to be some scaling factor multiplied by, we just need to find one that works, right? So 1 works in this case, right? That's pretty easy. 1 and 1 works because 1 times negative 4 plus 1 times 4 equals 0.
Oh.
And the second row, it also works. It should work for both. You only really have to do one, but it's kind of good to do multiple to make sure that you have it correct. 1 times 1 is 1. Negative 1 times 1 is negative 1. So 1 minus 1 is 0. And it should work for both rows. Okay, so you've got your eigenvectors and your eigenvalues and a boatload of confidence and good advice about Tulsi ginger tea. All right. Have a good weekend.